In this lesson, we're going to learn another technique used for factoring polynomials called the difference of two perfect squares. Let's begin today by talking about what the perfect squares are. The perfect squares are numbers that are created by squaring another number. 1 squared is 1, so 1 is a perfect square. 2 squared is 4, so 4 is a perfect square. 3 squared is 9, so 9 is a perfect square. 4 squared is 16, so 16 is a perfect square. 5 squared is 25, so 25 is a perfect square. 6 squared is 36, so 36 is a perfect square. In fact, all of the numbers that are circled in red on this screen are perfect squares. You should know all of the perfect squares from 1 to 225. A good way to learn these is to write them out several times on a paper. That repetition will put them into your long-term memory. Variables can also be perfect squares. X times x is x squared, a perfect square. X squared times x squared is x to the fourth, a perfect square. X to the third times x to the third is x to the sixth. X to the sixth is a perfect square. X to the fourth times x to the fourth is x to the eighth. X to the eighth is a perfect square. In fact, a variable with any exponent that is an even number is a perfect square. It's important to familiarize yourself with these, so please take a few minutes to do so. Now, let's begin with a brief exercise before we get into factoring. Here are three pair of binomials, x plus 5 times x plus 5, x minus 5 times x minus 5, and x plus 5 times x minus 5. Copy these three pair of binomials down and multiply them together. Please pause the video here, and when you're finished, come back. When we multiply, we use the distributive property. When we multiply x plus 5 times x plus 5, we end up with a trinomial x squared plus 10x plus 25. X minus 5 times x minus 5, we follow the same process. We use the distributive property, do our multiplication, combine like terms, and the result is a trinomial x squared minus 10x plus 25. The third example, however, is important for today. X plus 5 times x minus 5. When we multiply them together and combine like terms, we end up with not a trinomial, but a binomial, x squared minus 25. That makes this a very special case. Notice the two binomials. Both of them have x, and both of them have 5. The difference is the first one is addition, and the second one is subtraction. When we have two binomials that are almost identical, with one being addition and one being subtraction, we have what is called a conjugate pair. And the fact that they multiply into a special binomial makes them very easy to use for factoring. If we multiply any conjugate pair of binomials, what we'll end up with is a perfect square minus a perfect square. X plus 2 times x minus 2 multiplies to x squared minus 4. Notice that x squared is a perfect square, and so is 4. Those two are connected by subtraction. If we multiply x plus 10 times x minus 10, we also end up with a perfect square minus a perfect square, x squared minus 100. That means whenever we have a difference of perfect squares, a perfect square minus another perfect square, we can factor them into a conjugate pair. In the first exercise, x squared minus 4, we see that we have a difference of two perfect squares. X times x gives us x squared, and 2 times 2 gives us 4. So the original binomials must have been x plus 2 and x minus 2. In the second exercise, we have x squared minus 100. Again, a difference of two perfect squares. X times x is x squared, and 10 times 10 is 100. Therefore, the two binomials must be a conjugate pair, x plus 10 times x minus 10. We can generalize this by saying that a squared minus b squared, two perfect squares, factor to a plus b times a minus b. It's important to note that the operation between these two perfect squares must be subtraction. If it is addition, this technique will not work. Let's take a look at some examples. Our first example today is the polynomial x squared minus 36. We want to factor this. The first thing we always look for is a greatest common factor. Here, we have no greatest common factor. Then we look to see if we have a difference of perfect squares. We do. X squared is x times x, and 36 is 6 times 6. These two terms are connected by subtraction, a difference of two perfect squares. I can write this as a conjugate pair of binomials x plus 6 times x minus 6. In exercise B, we have another binomial, x squared plus 36. Again, the first thing we look for is a greatest common factor. There is none. Then we check to see if we have a difference of perfect squares. X squared and 36 are certainly perfect squares. However, they are not connected by subtraction. So this is not a difference of perfect squares. Since neither of these techniques apply, this polynomial is not factorable. Here are two exercises for you to try. Please pause the video here and see if you can factor these two binomials. In exercise C, the first thing we look for is a greatest common factor. There is none. Then we look to see if we have a difference of two perfect squares. X squared is a perfect square, and 49 is a perfect square. The two terms are connected by subtraction, a difference of two perfect squares. We can factor this into a pair of conjugate binomials, x plus 7 times x minus 7. In exercise D, we first look for a greatest common factor. There is none. Then we look to see if we have a difference of perfect squares. We do have two perfect squares, but we do not have subtraction. This is not a difference of two squares. Therefore, this binomial is not factorable. Sometimes we might have a number in front of our variable. Here we have 49x squared minus 81. We follow the same process. First, look to see if there's a greatest common factor. There is none here. Then, look to see if you have a difference of two perfect squares. 49x squared is 7x times 7x. 81 is 9 times 9, and they're connected by subtraction, a difference of two perfect squares. We can factor this into the binomials 7x plus 9 and 7x minus 9. In exercise F, we have the same perfect squares 49x squared and 81, this time connected by addition. The first thing I check for is a greatest common factor. Here, I have none. Then I look to see if I have a difference of two perfect squares. I do have perfect squares, but not a difference. This is a sum. Therefore, not a difference of two perfect squares. This binomial is not factorable. Here are two exercises for you to try. Please pause the video here and see if you can factor these two binomials. In exercise G, the first thing I look for is to see if I have a greatest common factor. I do not. Then I look to see if I have a difference of two perfect squares. I do. 25x squared is 5x times 5x. 36 is 6 times 6, and the two terms are connected by subtraction. This binomial factors into 5x plus 6 and 5x minus 6. In exercise H, I'll follow the same process. First, look for a greatest common factor and see that I have none. Then, look for perfect squares. I have two perfect squares, 25x squared and 36. However, they are not connected by subtraction. This is not a difference of two perfect squares, and therefore, this binomial is not factorable. In exercise I, once again, we're looking to factor. Notice that we do not have a greatest common factor, but we do have two perfect squares connected by subtraction. X to the fourth comes from x squared times x squared, 49 from 7 times 7, and 100 from 10 times 10. So we can factor 49x to the fourth minus 100 into 7x squared plus 10 and 7x squared minus 10. Exercise J is for you to try. See if you can use example I as a guide to factor part J. Please pause the video here. Let's see how you did. We have a difference of perfect squares. 8m squared times 8m squared gives us 64m to the fourth, and 9 times 9 gives us 81. The terms are connected by subtraction. A perfect square minus a perfect square, a difference of two squares. We can factor this into a conjugate pair of binomials, 8m squared plus 9 times 8m squared minus 9. Exercise K is an interesting one because people often forget that 1 is a perfect square. But we do have perfect squares here. 1 times 1 gives us 1, and 6x times 6x gives us 36x squared. The two perfect squares are connected by subtraction, a difference of two squares. Notice that the 1 comes first and the 6x comes second. When you write your binomials, you have to write this as 1 plus 6x and 1 minus 6x. If you wrote them the other way, they would actually multiply to 36x squared minus 1, which is not what we started with. Finally today, we'll end with an example that'll give us a preview of what we'll be looking at next time. Remember that I've said you always have to look for a greatest common factor first. And in exercise L, we do have a greatest common factor, 3. When we factor the greatest common factor out, we have 3 times 25x squared minus 16. And notice in the parentheses that what we now have is a difference of two perfect squares. 5x times 5x is 25x squared, and 4 times 4 is 16, connected by subtraction. We can split that parenthesis into two separate parts, 5x plus 4 and 5x minus 4. Don't forget the 3 out front to give us the complete factorization of 3 times 5x plus 4 times 5x minus 4. And so now you know everything that you need to in order to factor a difference of two perfect squares into a conjugate pair of binomials. Remember, you can find more information about factoring in Mr. Dory's Algebra Handbook, available on www.dorypublications.com.